Good morning. Welcome to the John Chappell Science Chat for November the 3rd, 2018. I'd like to welcome everyone. Franklin is on vacation, and I think he will be away next Saturday also. So I will be your moderator for today and next Saturday. And like to, we didn't have any volunteers for doing a program, so I picked one from my various talks I've given in different places around the world. And the one that I'm going to share with you today is related to the scientific method. And I'm going to give a little bit of a history of the scientific method. And then many of us have developed various theories, and we are sort of competing with one another for that. And the question is, do we agree on a scientific method? And what is the benefit of various versions of the scientific method that have been promoted over time, from the ancient Greeks to the time of Isaac Newton and to modern times. And we'll be talking about the axiomatic method of the ancient Greeks, the combination of the axiomatic and the experimental method that Isaac Newton promoted. And then we'll talk about the existential scientific method, starting about the 1860s, and then the postmodern scientific method, which is what is being used and has been used since about 1960. So,
excuse me, can I interrupt a moment?
Sure.
Going back to the fact that Franklin Hughes on vacation.
Yes.
The email notification was only sent today, and I'm sure that's probably why there's such a low attendance. And it said in the email that Franklin will be away for 3 weeks.
For 3 weeks? Okay. I haven't read my emails yet.
But unless the notification and the email is sent out, earlier than Saturday, you're going to get a very low attendance.
Okay. I appreciate that. I'll try to get that out for the next time. I don't have access to the system we use for putting it out, but I can just take one of the emails that has been sent out and send it to the same people. And so that'll probably work. Appreciate that comment. We like to have, I guess, as many people as possible for some of these meetings. Let's see. I guess we can start. Let me see if I can get this sharing to work. Can everyone see the PowerPoint presentation, the history of scientific method? Actually, it should be history of the scientific method. But...
Yeah, I can see it.
Okay, good. Because my second computer is not working too well here, so I can't see the whether or not you're seeing it. Well, that's great that you can see that. So what we want to do is we want to look at the major versions of the scientific method. I'm sure there were minor versions or less well-known versions that probably came up from time to time, but we want to look at these. So the first one I want to cover is the axiomatic scientific method. And see if I can get this a little higher up on the screen. Can you see the bottom of the screen where it says the last little circle, theorem/theory? Oh, there we go.
Yes.
Okay. So the axiomatic scientific method was the method of the ancient Greeks. And this method was based on logic. And what they did, this held for all of natural philosophy. So they observed patterns whether it was in algebra, geometry, physics, whatever, they observed patterns, and then they used inductive logic to come up with an axiom. And an axiom is what we might call an assumption today for your theory. And they observed things in nature, and with a straight edge and compass and counting with, and so they were reasonably successful in geometry and algebra, but not so successful in what we would call physics or regular science. But they had two sources of information: observations that they made with their own eyes and ears and those type of things. Then they had their intuition, and then they used logic to come up with a set of axioms. And then by using a second form of logic called deductive logic, they deduced a theorem or a theory, and from those axioms. Now, if anyone disproved one of the axioms, that disproved the theorem or the theory. And what you would do if an axiom, let's say the axiom was incomplete, and you modified it, and it came up with something more elaborate, more detailed than the previous one, in order to agree with what you observed. They would then substitute, let's say they had axiom 3 there, they would substitute a revised version of axiom 3, and then they would use deductive logic and come up with a revised version of the theorem or the theory. And that worked pretty good for algebra and for geometry. And so they made a certain amount of progress that way. Then people started looking at the axiomatic method, and they found various limitations of it. Euclidean work turned out pretty well in geometry, but in physics and other areas of natural philosophy, the ancient Greek natural philosophers were not able to discover the appropriate axioms or postulates by just observation and their intuition. And this was due to the fact that the axiomatic method is a method of logical organization of abstract proofs of theorems or theories, but not a very complete method of postulate or axiom discovery of objective reality. And we would say that a better method would be not just to observe, but to perform experiments. But they didn't do it that way, although you might say in geometry, because they used a straight edge and a compass, they were actually performing experiments in geometry. But anyway, they did better in geometry because they used a straight edge and compass and used that as part of their ability to find appropriate axioms to develop the theories of geometry. So there are a number of people made criticism of this work of the ancient Greeks, and perhaps one of the most significant people to analyze that was Isaac Newton, and he promoted the empirical method of axiom discovery. And a quotation of his from his book, Mathematical Principles of Natural Philosophy, which from his point of view was his most significant work. Now we think of him because of the force of inertia and the force of gravity, having developed those, but in his publication, Mathematical Principles of Natural Philosophy, he indicates that that work is incomplete, and he outlines the method for doing better. And the emphasis that he puts in that book is that the purpose of philosophy seems to be to find the forces of nature from the phenomenon of motions, and then to demonstrate other phenomena resulting from these forces. And for instance, today, if you were go to college or high school, you would be told, well, the forces of nature are the electromagnetic force, the force of gravity, the strong interaction force, the weak interaction force. And so they would say there are at least four fundamental forces. And so from what Newton said, that you should proceed. And he says, many things lead me to have a suspicion that all phenomena may depend on certain forces by which the particles of bodies, by causes yet unknown, either are impelled toward one another and cohere in regular figures, or are repelled from one another and recede. And he said, since these forces are unknown, in his day, they knew a little bit about gravity, and they knew a little bit about Coulomb force, static force between charges, but they didn't know very much. I guess you would say the best that they might have known was that the force, both the force of gravity and the electromagnetic force, were 1/r² type forces. And he said in his book, I hope that the principles set down here will shed some light on either this mode of philosophizing or some truer one. Now, what he said in his book, and this is not an exact quote, but it's very close. He said that you should perform experiments and develop empirical laws. Now, in his day, those laws were Kepler's laws. There were 3 laws. And he said those laws are now going to become your axioms. And so from those laws, you want to develop what the force is. Well, Kepler's laws don't even talk about force. But if you have the correct force that's causing the planets to go around the sun, well then you should be able to derive Kepler's laws. And that is what Isaac Newton did. And but just to put things in perspective, he was asked, when you write down the force of inertia, in order to make it an equation, you knew that the force was proportional to the acceleration. But you put an equal sign there, and then you put a constant, which you called mass, m. And then when you did the force of gravity, you knew that it was proportional to 1/r², and you knew that it was proportional to some property of each of the 2 bodies that were involved. And so you wrote down the equation F equals big G, the universal gravitation constants, times mass 1, gravitational mass 1, gravitational mass 2 over r². But when people ask him, well, what is mass? He said, I don't know, but we should learn eventually by performing more experiments in more areas. And then, since, for instance, the force of gravity and the electromagnetic force, Coulomb force, are both 1/r² forces, we should try doing things like, can electrodynamics explain gravity, or can gravity explain electrodynamics, and that sort of thing. And so then we can progress to a more general force law. And but unfortunately, he lived at a time when we didn't have very many empirical laws. But later on, we did, in electrodynamics, we developed 6 empirical laws. And following his suggestions, we should try to solve all 6 together, because the 6 equations involve 6 unknowns. And so with 6 unknowns, you should be able, and 6 equations, you should be able to get a solution. And but that wasn't done in his day. It was done in the days of Maxwell. And unfortunately, people did not like what Maxwell was doing. And so after he died, they changed, and they did it a different way. They said, well, we don't know what this general solution means. It had, and this was, they didn't use these words, but it had what we call relativistic terms in it, and they didn't know what that meant, and they'd never heard of relativity theory, because this was 50 years before Einstein came along. And so they threw away Lenz's law, which causes that to be occurring in all their equations in electrodynamics and forces. And they didn't know what to do with some of the unknowns, so they came up with ideas that would discard those unknowns, so they could get the number of unknowns down to 4, and the number of equations they needed was 4 instead of 6. And so under Oliver Heaviside, they did that. Now, that did not agree with what Newton said to do, to make progress. So let's go and look at the next slide here. When Newton did his work, he combined the experiments with the axiomatic or logical method. And this is a picture here on the screen of the scientific method. And so you did observations, as we did before, you did deductive logic, and you came up with a candidate. And then you performed experiments to check out some of the ideas that your observations led you to. And you wrote your empirical laws in mathematical equation form in terms of physical terminology. Mass. What people considered mass and weight, was kind of a physical thing. And they considered in electrodynamics a charge would be a physical thing. And so they did that. And then once you had obtained your axioms in more precise mathematical form, you can now predict what you should see in various experiments. And so you test for 100% completion. There are certain types of data that cannot be explained by this axiom. And if the answer is, there's some that can't, then you go back to your definition of your axiom and you try to correct it and work better. Sounds good? Sounds good. Then you collected all these unique axioms to derive a force law. And then you use the force law to make predictions, and you compare those predictions to empirical data. And then you ask or try to predict the data in another field. Like, for instance, if I worked in electrodynamics, and I thought you could derive the force of gravity from then you would see if you could predict the force of gravity better than previous theories, because you have another field like electrodynamics where you have more complete information than you do in gravitational theories. And so you use logic and you see if you can predict that. And so that's what Newton said to do, but he didn't have all this data available, so all he could do was outline what you needed to do. And he thought that there was only one universal force law. And he thought that all these other forces that you're seeing in nature are just due to our ignorance, and we don't know enough about these other fields to even know, in the sense that they're related. But you could see that in the case of Coulomb's law and the force of gravity, both are 1 over r squared laws. And so there's a lot of similarity there. And so it may be that that has something to do with the fact that they come from one source. And so that was what Newton proposed. Now, before the time of Isaac Newton, there was Johann Kepler, and he discovered 3 empirical laws. The planets loop the sun in ellipses, with the sun at one focus. The line joining the sun and the planet sweeps through equal areas in equal amount of time. And the square of a period of a planet's orbit is directly proportional to the cube of the semi-major axis of its elliptical path. So that those 3 empirical laws is what Isaac Newton knew that his law of gravity and law of force of inertia must be able to agree with that had been developed in Kepler. And even though his work was not perfect, he was able to reproduce those 3. And so he satisfied a requirement of the scientific method. And unfortunately for Newton, shortly after he died, Phineas Bode came along and discovered a quantum law related to the motion of the planets around the sun. It's called Bode's law, and this is a more modern version of it. You see, it says the period of each planet is equal to the period of the sun, major axis of the planet. And there is a plot showing on the left-hand side of the sun, period, and then you see the all the planets, and you'll see that even Pluto, all the planets lie on a fairly good straight line on a log plot, which is a little, rough in a sense, and it makes things look better than they might be if you just did a straight plot. But it gives you the idea that there's something that's approximately right with this approach, and but Newton didn't see that, so he never modified his law, force of inertia and force of gravity, to take this information, this empirical law, into account. And not only does it work for the planets about the sun, it works for the moons about the planets. So in the second graph, you see the planet Uranus, and you see 5 of its moons, and they also follow this same Bode's law. And so now what is interesting is no one, as far as I know, has been able to modify the theory of gravity and the force of gravity and the force of inertia to explain this quantization. It still remains to be done. In fact, because of our current scientific method, which we'll get to, there's no interest in doing that because that is not the way we're doing science anymore. And so this remains a unusual data which nobody understands. And so that is what is happening right now in terms of gravity. But that's not all. We have started in the sun, and we have observed the velocity of the outer arms of spiral galaxies. Here's a particular one, NGC 6946. All of them do it more or less the same. In the spiral galaxy graph, excuse me, of rotational velocity versus distance from the center of the galaxy, 0. You see the actual observed data on top, and then below that you see the predictions of Newtonian gravity. And it's not only Newtonian gravity, it's also the predictions of general relativity theory, which follows the Newtonian gravity because these are not relativistic motions. They're much slower than that. And so there's not much of a change from Newtonian gravity to Einstein's general relativity theory. So there's something wrong with our theories of gravity because they cannot explain this data. And it's not just out in the spiral galaxies like the Milky Way or this NGC 6946. If you look at the next plot, we'll see that in our own solar system, just about our own sun, we put up Pioneer 10 and 11 to measure the force of gravity in the outer part of the solar system. And it's just like the previous plot. It doesn't agree with our theories of gravity. It doesn't agree with Newton's universal law of gravitation and his force of inertia, and it doesn't agree with Einstein's general theory of relativity. And so we have lots of data. And has anyone modified our theories of gravity to make them fit this data? No. You know what they did? They invented dark matter and dark energy to make it so that they could add something to our theories of gravity so that it would explain this data. And there's a little fudge factor. 94% or 96% of all the matter energy in the universe is dark matter and dark energy, and what we observe is only 4% of the universe. So the fudge factor is a factor of 25 in terms of mass. And no one has ever observed any dark matter or dark energy directly. I worked in accelerator experiments. We make all different kinds of elementary particles, and we have never seen any dark matter or dark energy. And we should be able to make some, and we're not. And so anyway, that is the way we're doing science. And the theories, none of the theories of gravity have been falsified because of their failure to explain this. So we would go back and try to do a new theory of gravity or a new theory of the force of inertia. So now, what did we do when we couldn't do this? We had to change the scientific method. So, starting around 1860, we did what was called the existential scientific method. And I have this, I showed this on the screen. This is quite different from the combination of experiment and logic, the empirical and the axiomatic methods that Isaac Newton worked with. What we do here is we make observations, we define a problem that we want to solve, and we formulate a hypothesis. Okay? Then from that hypothesis, we deduce predictions of what would be observed in nature, such as the force of gravity if you go out from the sun, or the outer arms of the velocity of the outer arms of spiral galaxies, um, and all that. And we have Bode's law. You know, we have these observations, and we make predictions, and then we gather data and perform experiments to analyze them to see if they are properly explained. If they're not, we go back and revise the hypothesis. If they seem to be explained well, we do gather more experimental data, and we reproduce the experimental data over and over again to make sure it wasn't an accident. We got data that agree with our theory. And so that is what we're doing now. But notice the role of logic is partially removed. We don't falsify a theory because it involves a hypothesis that's false or an assumption that's false. We don't even, in this scientific method, we don't even define assumptions. We just formulate hypotheses. But we have skipped half of the scientific method that the ancient Greeks and Isaac Newton used, and we're not doing very well. And we're not letting our scientific community and our people in general know there's something wrong with our theories. And like we just talked about, no theory that's currently politically correct can explain Bode's law, which is the quantization of gravity. None of them can explain the change in the force of gravity as you go out from the sun. And none of them can explain the properties of the outer spiral arms and the velocities and that sort of thing of spiral galaxies. And we're not told that, you know, the theory doesn't really work anywhere properly. We just told, this is it. This is politically correct. You learn this. And so people aren't looking for a solution. Well, the question is, what scientific method are we using in our own personal work? How do the various scientific methods compare? Which scientific method is the most rigorous? Can any scientific method that we've developed so far identify truth? How do you identify truth? Which scientific method should we use? Now, each of us who are doing work in science, we have to answer those questions for ourselves. And some of us don't even think about the question. And so they would say for this third question, can any scientific method identify truth? And they say, no, it's approximation. So it doesn't make any difference what your assumptions are. You just do what you do and see how much data you can or cannot explain. And so we're not worried if we can't, like we have a theory related to gravity and we can't explain the quantization of gravity, and we can't explain the way gravity increases as you get out further from the sun, and we can't explain how the outer arms of spiral galaxies move and their velocity and everything, and the radiation is coming off and all that kind of stuff. And so we just ignore the fact that we can't explain that because it's not important. And so that's what we need to talk about. So at this point, I think we should stop and have some discussion on what you think the scientific method should be that we're using. And that sort of thing. Let's see. Right. No. Okay. The existential method was changed, this is the previous one, was changed in about 1960. And we still have this, what's called postmodern scientific method. Now, the difference between the existential and the postmodern is the existential method is still based on the idea that all the fields of natural philosophy are grounded on truth to some extent. And so there's only one set of theories that is acceptable. And we have what we call the university. University, the name reflects this idea that there's one truth, and whether you're taking chemistry, uh, mathematics, geometry, chemistry, physics, astronomy, geology, all of them should agree on what's going on. But what they did under the postmoderns, they said, well, this is not working out too well. So we're going to separate all these fields into separate silos. We have a name for those silos today. We call them departments of the university. And we no longer have a university, we have a multiversity. And so, for instance, chemists discovered that the force of gravity is electromagnetic. Not only is it 1 over r squared, like electrodynamics, but they found that the force of gravity was due to the force between vibrating neutral electric multipoles. And they found this out in their laboratories, in chemical factories where they were making things, making various substances, and they discovered they were changing the force of gravity, and when they did that, it interrupted their chemical processes, and they had to find out why, and that's what they found out. Things were becoming much heavier than they needed to be. And so certain molecules would drop to the bottom and not participate in chemical reactions that they wanted to participate in. So, anyway, so what we have now is we have this astronomy, physics, geology, we have chemistry, all these different fields, and they are independent of one another. We have their own separate things, the parties that control what is in the silo. And so, for instance, in the physics side, we are not allowed to publish any articles in politically correct journals showing the chemist's experiments that show that gravity is related to electrodynamics. And and for instance, if you're going to measure the age of the Earth, you're not allowed to combine that. It's in other silos where, like nuclear physics, where they look at, say, radio halos in a minute, that's radioactive, to determine what the original nuclear isotopes were in that particular sample. And so you assume, oh, well, the Earth was molten for a billion years, and all the isotopes decayed away. So when you measure the uranium lead, we get an age of the Earth of 4.5 billion years. But if you look at the minerals that have the uranium lead in it, and you're asking the question, well, what were all the things that decayed the lead in here? And you say, oh, I can see the radio halos for the decay of all these short-lived isotopes, which were more common than the uranium, but they all decayed to the same isotope of lead. And you can see the data, but they never say that. They never even talk about it. And when you do, you're told you're unacceptable. You cannot come to our meetings and talk. It will not be published in our journal. As all the other people come to this conference where you're speaking is, and that sort of thing. So we find ourselves having problems in science because we're, we're short-circuiting the whole scientific method by this postmodern philosophy of science and the existential philosophy of science, which doesn't use logic properly. Okay, so I think that's the main part of what I wanted to communicate. So let's have some discussion about these ideas and see if we can help one another out in terms of our own personal approach to these things. Okay, so if you want to unmute yourself and talk, you can. Any discussion on this?
Are you willing to entertain an ether, a model of gravity and electromagnetism?
Yeah, sure. For instance, in gravity, if you have an ether model, can you explain the way the force of gravity is not due to what you would call pushing or pulling gravity exclusively, because those cannot explain the quantization, they cannot explain the deviations from the force of gravity doesn't work the same way as you get out farther from the sun, and also at the edge of spiral galaxies. So what you have to do is be able to predict what is observed. So my question is, how can you do that with the ether type of approach?
Well, you're right. It's more of a common sense type of thing. Well, basically, you start with the idea that what came first was space, and then space was there was a universal oscillation of space, and then this oscillation led to oscillational fatigue of elemental point localities of space, and then this led to oscillational fatigue, led to yin-yang combinational pairs, which in reverting to singleton units broke the perfect symmetry of space, because by reverting to singleton units, the fell out of phase with the oscillations, and so that created a vibrational universal ether composed of elemental point units, which from that would be so fundamental and elemental that they would be not only constitute a universal matrix, but also a universal matrix in space, but also be the fundamental ingredients of everything from then on, including larger units such as electrons, photons, atoms, and so on. Well, this produces a very good model for quantum entanglement, for one thing, but also it leads to a model of gravity, which is that there would be an elemental ether unit continuum that extends across from solid bodies to the space in between the bodies, which is vibrationally resonant. As the outward vibrations make contact, they are resonant. And then this resonation would be universal. It would be not only inside the bodies, which is more dense, and a lot of electromagnetism in the atoms there, but this would be a process that would also extend into the space between the bodies due to this universal elemental ether unit continuum. And so therefore you would have this simulate the electromagnetism inside the bodies in the arc space between the bodies. And so this would be a conceptual model, I grant that, but still it makes sense.
So what would you say of these scientific methods that I have presented, which of them would you say you're following, or are you doing a totally different?
No, you'd have to call on your phone.
Well, this is different from anything else, really.
Well,
It's just it makes common sense, and it explains quantum entanglement also, which conventional science does not do. Because if you have the two quantum units are composed of the same elemental unit, ether units, as the intervening matrix is composed of the same elemental units, then you would have quantum entanglement would be due to packets of elemental ether energy units which have the same vibratory pattern and would enable the quantum units to communicate across the matrix, the ether matrix, because they are made up of the same elemental units.
But getting back to the scientific method, what method are you using, and how can you define it?
Well, it's completely different. It doesn't use the scientific method. It uses concepts of that are not demonstrable empirically, except if you could produce an selectively etheric energy field, you could probably produce levitation or decreased density within the system if you had a way of producing an etheric energy field, because the ether is so rarefied we can't detect it, and all we can do is observe the the downstream effects on quantum systems, and we don't really know what's going on underneath that surface.
So are you saying that your method is not based on logic nor performing of experiments for the most part? It's based on intuition.
I would say it's based on logic and intuition. It's not based on empirical observation as much. Although I still submit that it's a better explanation for quantum entanglement than any quantum model is. And the model of gravity would be common sense, but it's not something I could prove, experimentally. The only way you could do it would be if you could produce an etheric energy and see if it has etheric effects on a quantum atomic system.
Now, I know you put a lot of emphasis on quantum. Are you aware that using the scientific method of Isaac Newton based on experiment and logic, that you replace the quantum theory with a physical basis for quantum effects, not a mathematical basis that the quantum theory of the Copenhagen version of quantum mechanics put forward, which is what they teach now in all the universities. And and you can do that because NASA performed experiments, for instance, with atoms, both hydrogen and helium in outer space, and they discovered that the theories of quantum mechanics for the atom, the Bohr model, the Schrödinger model, and the Dirac model, they all fail to predict 50% of the emission spectral lines and absorption spectral lines of hydrogen and helium, the synthesis atom. And that, according to even the existential philosophy of science and the postmodern philosophy of science, is enough to falsify the theory, but they won't do it.
Well, I could submit a hypothesis that all these effects are still to be defined secondary effects of the ether of space.
Well, we've already measured it. We have the measurements of these spectral lines are the most accurate measurement ever made for atomic spectral lines. And
no, I mean explaining the aberrations from quantum theory.
Yeah,
would be according to something that we still need to define about the ether.
Yeah. Well, if I have a theory that can only predict 50% of the phenomena, is that a good theory?
Well, you need to add the ether to it. That's what I'm saying.
Yeah. But what I'm saying is, there is a non-quantum mechanic theory based on physical properties of matter that does explain all of these properties of the atom. And but modern science says we don't want that. We want our theory that we have already. We don't want to change. And is that the way we should do things in science? In other words, when we went to the postmodern philosophy of science, we don't care what your experiments show. We're going to just have our own theory. That doesn't work for that data. And we know it doesn't work. And that's why we made silos, and you cannot publish your work in our silo. And we won't publish our work in your silo. And like, for instance, the age of the Earth, just to give you an example, in the Big Bang theory and in the current geological theories, the age of the Earth is 4.5 billion years. But from nuclear physics and looking at radio halos, the age of the Earth is between 5,000 and 10,000 years. And that's with 20-some nuclear decay methods for measuring the age of the Earth. They all agree on that when you properly analyze it. If you don't do that, they all disagree. You only have 3 that says the Earth is old, and the rest of them say it's young. Like carbon-14, for instance, says that the Earth is young. And so it's crazy, but how do we deal with that? And what you're doing is you're coming up with common sense science of another way of looking at it. And I suspect that if you're successful in predicting things, that there's some commonality between one approach and another approach that enables a partial prediction and agreement with theory of experiment. And but would you say you're in an early stage of development or a more mature stage where you can make many mathematical predictions?
Me, I can't do any mathematics on this because we're unable to detect the ether. It's too rarefied. We can only detect secondary effects such as quantum entanglement, or if you could produce an etheric energy field, you could probably demonstrate levitation or decreased density within the test system. So those would be 2 ways you could derive evidence for an ether.
Were you aware that quantum entanglement has been explained by the work of William Cooper at the University of California at Berkeley? He measured 13 properties of electromagnetic fields, and he was able to show that some fields cannot be fielded, and they can all electromagnetic fields have tensile strength, which means they form a continuum. So you've got to explain the electromagnetic field and having tensile strength in the continuum. That's very similar to an ether. You know what I mean? And he showed that entanglement results certain fields that cannot be shielded, and they are continuous with tensile strength, and they produce these effects that we call quantum entanglement. You can predict what they produce.
Well, I guess it's one theory against another. That's all I can say. I don't see how quantum forces, which fields, waves, vectors, spin, can explain quantum entanglement. Logically, I think my model is better.
Well, they claim they can predict all of the experimental results that we've made so far, and they don't need a separate theory of an ether. They just use the theory of electrodynamics, which they already have. You know, are you saying that electrodynamics is going to be replaced by your ether?
Well, electrodynamics is a secondary effect of the ether. The ether operates vibrationally, and the quantum systems operate via fields, waves, vectors, spin, and so on. It's a different thing, and
so basically, that your theory is fundamental.
well, vibrational is perfectly linear. It's a perfectly linear resonance, and that's why I'm saying it's better to explain quantum entanglement, because the quantum forces are not linear.
Okay, do you have any other comments you'd like to make about your approach and the scientific method and the role of logic and the role of experiments?
I guess I don't know if you can hear me. I'm on the phone.
Yes, we can hear you.
You do hear me. Okay. I'm Paul Schroeder.
Okay, well, right ahead.
And I guess I can make a couple brief comments about a little bit toward what Michael was just talking about, and that he's got this ether that, and I had presented last week a piece of my theory that says that there is an existence to all of space, but it's all created by the radiation passing through everywhere. And the ether is a semi-similar concept that, you know, every place exists, every point exists and has something that creates it. And Michael's saying, well, his theory is vibration and it's linear. Well, you know, my system would be linear, and that everything's moving at speed c everywhere, so that's linear. And you know, his vibrations can be the existence of all these radiation pieces bumping into each other and creating every point. Now, that's what I have to say about Michael's approach. But I want to also talk about the Bodhi system a little bit. It's been a long time since I've looked at that. My system of gravity, as you know, is a pushing gravity, and it works in such a way that individual lines of all this gravity penetrate something like, say, the sun, and when they come out the other side, they pick up the rotation of the center body, so that they become the driving force of the whole universe, because they curve a little bit. And that curvature, ultimately, when it comes to other orbital pieces, say around the sun, that curvature of the gravity at that point pushes the orbital in its basic orbital line, semi-offsetting the gravity that comes from outer space that pushes the orbital toward the sun itself. So you've got those two offsetting functions, and the amount of the push of this rotation depends on whether a particular line, for example, of radiation went right through the equator of the sun, or it went through a higher altitude part of the sun or lower altitude sun, because the amount of rotation that's given to each line is where it goes through the sun, and there's much more right at the equator line. And now the amount of push you got, say, on the Earth that pushes it in its orbit is a sum of all the radiation that does penetrate the sun and actually is in such a line that it will actually impact Earth, either at the Earth's equator or above or below. And you have to sum up all of those pieces. So this thing is never mathematically determinable. And a piece of the whole thing is that if Earth was say twice the size, it would be hit by a few more curved radiation from the sun, and its orbit would be slightly different. Or if the Earth was just a moon-sized thing, its orbit would be different also. And the farther out you get from the sun, and first of all, it's important that that all the planets are on basically the equator of the sun, because that's where your main push to the left comes from. And when you get out further, it depends on the size of the body that's being pushed on, what exactly you're going to get for your rotation. But the fact that the sun's rotation is a factor is a very important piece of why Bode's law works. So anyway, that's there's a lot to this, but I don't have it in front of me. So that's what I see. I guess that's all for now.
Anyone else want to make some comments or support for their own approach to science, whatever their particular theory is?
I guess I just want to say, Michael, that is a little bit interesting what you just said. I'm not sure if you touched on that last Saturday. I'm sorry I missed last Saturday, but that is kind of a interesting, I guess, aspect of Bode's law, that it's affected by the spinning of the sun. I'm kind of wondering, along that same concept, does that explain the precession of Mercury also, or does that not have any effect on the precession?
I don't know if you're talking about what I just presented. The actual rotate. I've got something somewhere on that thing for Mercury, but it depends on the size of the body being pushed and whether the beams hit in such a way that they go through and give it rotation, or whether they don't. It usually creates rotation of the body counterclockwise. Obviously, for Venus, it doesn't, because it hits at a different angle. But yeah, I've got something. I had something somewhere that talks a little bit about the Mercury.
Mercury's precession occurs at a 13-year regular interval. Therefore, it seems like it would be just a normally due to ordinary gravitational forces, regional gravitation, not due to anything on these related to our alternative theories.
Yeah, I agree.
Okay.
I have a question. In our solar system, not all the planets rotate in the same direction, like clockwise or counterclockwise, and some of them go around the sun in the opposite direction. Why is that?
They all go the same way.
No, they don't.
Yeah, I think it's Venus that might go different. That is a good question. I think, is it Venus? I think, Bill, that goes the opposite.
I'm not sure, but I know there's at least one planet that does that. And so the question is it was it formed by the same process that did the others, or was it from outside the solar system and it came in and joined later?
Well, everything rotates counterclockwise around the sun. Everything everywhere rotates counterclockwise. That's a basis of the universe. But once in a while you get a rotation as opposed to revolution. It's revolutions that are always counterclockwise. You get a rotation that's not, in case of Venus, it's backwards because of how the gravity hits, whether it hits on the closer side to the sun or on the farther side from the sun on average. Most rotations are also counterclockwise.
I agree, there's a majority of that way. Other comments that people would like to make? Okay, we have been talking about the scientific method. It is interesting that the people who have talked about their work since we finished the first part of the presentation, they are not using the regular scientific methods that have been documented and promoted over time, but they're trying to use what you might call a common sense or intuitive type of approach. And so is that the future for us in science? So can we, using that method, define a reliable scientific method, or do we have to continue to depend on intuition and common sense without having mathematical rigor and prediction? How do you think about that?
I think it's always good to question the different methods. Otherwise, how do we progress? I guess. I kind of prescribe to. I think I would consider it a scientific method that was developed by Glenn Borkert, and I don't know if you've ever read the 10 Assumptions of Science, but they're basic 10 axioms that he kind of set forth, and he kind of explains why these axioms are good to use for scientific methods, and they're pretty common sense, as well as I think they're very very well thought out, and they do make sense intuitively and physically, and they seem to prescribe to the normal rigors that we put scientific methods through. But I don't know, I'm kind of curious if anybody else has ever read the 10 Assumptions of Science, and if so, what they think of it.
I have a favorite series of writings that is basically Henri Poincaré, who was recognized while he was living as one of the most important natural philosophers, scientists in Europe. he started a field of natural philosophy called metatheory. Metatheory is the theory of theories. And he developed a certain number of logical theorems in metatheory. And those theorems falsify many of the politically correct theories today because they don't have a proper logical basis. When they remove the axiomatic method from the scientific method, none of their theories could be shown to be true. But that is very interesting, and I've mentioned before on this chat that I went to the University of Maryland where I got one of my degrees, and to the library, and I asked to see some of these books that he published on meta theory, and they told me that they were not allowed to give the book to any person, including the head of the physics department or the president of the University of Maryland, that it was outside the silo they were allowed. And but anyway, they had a number of theorems, and in my book, The Universal Force Law, Volume 1, I've published a number of the theorems that he had and applied the theorems to various theories. And, for instance, one of the theorems is no two force laws have the same form, like R squared. And if you have two theories that are one over R squared for force laws, then one is false, or maybe both are false, but both are not true. And and also you cannot use the same constant in your equation for two different theories because the constants are unique to that particular field or theory. So if I have electrodynamics with a constant C, and I have special relativity and general relativity with a constant C, well, only one of those three could possibly be true. And if I have quantum mechanics with a constant C also, only one of them could be true. And according to the theorems, the meta theory, follow that tells you that there is something wrong, there's something incomplete. And in the work that I have done in electrodynamics, I took all these theorems and said, okay, if these theorems are valid, and I cannot see the proofs of the theorems because they have been outlawed in Europe and America, and I don't know of a place to go where I can get the books that were published, but anyway, looking at that, I tried to see if electrodynamics could be the more universal force. And I found so far that the theorems of Henri Poincaré seem to be valid. And the problems in electrodynamics, why relativity theory was invented and quantum mechanics and all that, is because the complete set of the empirical equations of electrodynamics were not used, and they were solved in terms of what's called the vector potential A, and not in terms of the energy potential. And the energy potential gives you a much more complete theory. And that's one of the things that Newton pointed out was the energy potential is a physical thing. And if you use things like vector potential, it's non-physical. But you cannot get and by the way, the vector potential is falsified by the discovery of magnetic monopoles. And believe it or not, I suspect most of you, if you have refrigerator magnets on your refrigerator, have magnetic monopoles, and we never knew it.
Yeah, that's interesting. I pasted a link in the group chat that talks about, or that actually you can download one of his books called Science and Method. I'm not sure if that explains some of the concepts that you're talking about, or he explains it in that book.
It talks about the theorem. It defines the theorem, but I was interested in the proof of the theorem.
Okay.
And that is what I can't get hold of. I do have quite a few books on Poincaré, and so I know about a lot of the theorems. I don't necessarily know all of the theorems, but I know quite a few, and I've used that myself. But I would be much happier if I could test
Hello?
the validity.
Bill?
Yes?
Bill, here is Postmodern. May I ask you a question?
Yes?
I remember I sent an email to Dennis Allen and you regarding the your referencing of the Poincaré's work in your 2016 paper. I took a look, and there is only some part related to the special theory of relativity. Do you have maybe another reference that you are talking about? There is no any mentioning of 1 over R squared, any kind of, nonlinear combination of nonlinear theories or whatever.
In electrodynamics, the what I call relativistic, special relativistic functions like square root of 1 minus v squared over c squared and that sort of thing, they all come from Lenz's law. And
but in the Poincaré's work, the error in French, do we have original in French or we have some translation in English?
Well, I don't have. I can read French, but I don't have the.
Yeah, but in those books, number 9 or whatever, that you indicate pages and so on, there is only talk about special theory of relativity. There is nothing of the kind that you have been presented in your paper. Could you please check that reference and maybe provide some other?
Okay, in my book, I think it may be properly done, but
okay, but it will be fine if you would send us. As a correction of information in your paper or whatever, just to spare us buying book for that information.
I sent Andre Assis to France to look for that, and he said he couldn't get it out of their universities, even though he was, had status at the universities.
No. There is no problem in the books. The books are accessible in the internet. Just type in Poincaré and Euler in French.
Yes, but not the book.
And you get it.
Of the theorems in meta theory. There's not a single book on the internet that has that.
But so could you provide that copy of it to us or what?
I have a copy of every book by Henri Poincaré that's for sale on the internet. So.
No, it is Bill. It is difficult to understand in this way. Could you please send an email about that to advise, please?
Okay.
Thank you. Because I cannot understand all the data. Even when you're talking, it's difficult to get it. Thank you.
Sure. Okay. Other areas of discussion that we might want to do? Are there any people present that would like to be the speaker, or we'd like to, if we could have PowerPoint, it has to be a PPT PowerPoint presentation, not the latest.
I'm not hearing you. Can you repeat?
Okay. I'm looking for speakers to present next week. After that, and,
I still have. I don't know. My phone's giving me trouble, I guess.
I'm sorry about that.
No, it's got to be on my end.
The other thing is, I would like to have something sort of like I did today, a few slides for PowerPoint that make it up to PPTX format current. And the reason the Hughes does not support sharing of the PPTX. Most versions of PowerPoint can do both. But okay. Are there any more topics you would like to discuss? Any more points of view that you would like to give support to while we're here? I feel like we're like scientists, stones sharpening one another. You know what I mean? It helps us see things that maybe we need to pay attention to. And I myself have profited a lot from that. And none of us know. And we often ask someone who does know, and that helps. Okay. Well, if there's no more comment for today, I will end the recording. Is you want to say something else before I end the recording?
Yeah, I sent you an email just before this started. It's Paul Schroeder. I do have a paper that I can go through perhaps next week if you want. If you're looking for something to do.
Okay.
About the electron.
Okay. If you'd like to do that, that would be fine. And
if I can get on with it, I've had a terrible time here with phone systems and headphone, and I don't understand it all.
There's a lot of feedback coming from, and are you using a computer that has a built-in microphone, or are you using one that just plugs in?
No, I don't have the microphone plugged in because that interferes with the headphones, which also don't seem to be working today. Microsoft 10, there's a lot of complaints about the fact that Microsoft 10 is not handling headphones at all anymore.
Well, I have Windows 10, which I think is what you mean by Microsoft 10, and I find that when you plug in a microphone or a headphone, you have to turn off the other one that you have, or it will give you a lot of.
Yeah, I can't hear a thing in my headphones.
Well, you don't have speakers built into your computer. Is that right? You don't have speakers?
Yeah, I don't have those plugged in because I was trying to do the headphone, and I'm ultimately it managed to work after a while last week, but not this week. My speakers are not plugged in.
Okay. Well, if you next Saturday, if you are going to speak, which we hope you will, call in about a half hour early, and we'll work on that and get all that working out for your benefit. And
Yeah. So call the invite number. That's what I'm on the phone today on the call-in number.
Yeah. You don't have a computer with views on it?
Yeah.
You do.
But it's not handling the headphones so that I can hear anything.
Well, I can work with you on that, perhaps.
Okay. Something made it work after a while. A lot of fooling around last week. I don't know what it was.
I have to do the same thing every week. I don't do it every week, so I forget how to do things for a while, and then I have to learn all over again. So
yeah. Okay.
Okay. Well, Paul, we'll look forward to that for next week, and if you could send me the description you would like me to put out to all the other people about what
I did send it to you.
Great.
It's attached.
I'll go ahead and do that. If I show my mail, it comes up on the screen, so I'm not looking at my mail while we're talking here. Okay. Well, if that's everything, then we will look forward to hearing from you next week, and hopefully we'll get the information out earlier so that more people will be able to attend. And I appreciate the comments of everyone, and I hope that nobody is upset from the comments we made, but that we show good respect for one another, and even if we don't agree with everything you have to say, but the thing I find important is that I learned some new things which I apply to my own work, and I've had wonderful results as doing that from a fellow named Dennis Chappell. And so I hope that all of us can find something to benefit, and that's why we're coming, and we want to learn more and share more. And so that will be our goal in the next 2 weeks, when I'll be the moderator, and look forward to hearing from you then. I'm now going to press the stop recording button.